Hello everyone, Professor Dustin here, and this video is going to show you a solution to the whiteboard spring from a table. So in this whiteboard we have a spring sitting on a table. We know that the height of the ball, the original height of the ball, is 1.2 meters. So what's supposed to be shown by the picture is that the height of the ball from the floor is right there. So the ball right now is actually not at that height. Right now the ball is depressed a distance 7.5 centimeters. The mass of the ball is 3.5. Spring constant is 3660 for the spring. And we just want to know the motion of the ball in a few different places. So first, what is the speed of the ball when it leaves the spring? So right after it goes from this compressed location to right here when it leaves the spring. Then we want to know the maximum height of the ball, that is the height right there, and then how fast is the ball traveling when it hits the ground, so when it lands here. So what's tricky about this problem is basically the height to use for each part, because the ball is going to be traveling up and down, up as it leaves the spring, so it travels a short distance upwards, delta x, before it leaves the spring, and then it travels some unknown distance up, and then it falls a full distance to the bottom, which includes the height of the ball. So really what we have to be careful about is where the zero for gravitational potential energy is. It's very common to set the zero at the floor, and that's kind of why I indicated this H, as I was thinking a lot of people would want to set the zero of potential energy at the floor. But of course you don't have to. You can set the zero for potential energy anywhere you like. So let's see in detail what that means as I try to do the problem. So this is definitely a conservation of energy problem because I have a spring. I want to know things like how fast the ball is moving when it lands, how far it falls. So that all suggests that we want to do conservation of energy. There are three possible sources of energy in this problem. The kinetic energy of the ball, because the ball is moving, the potential energy of the spring, because the spring can hold some potential energy if it's compressed, and potential energy due to gravity. So I'm just going to write the total energy as the sum of the three individual sources first before I start assigning values to any particular form of energy. So there's my kinetic energy final. There's the potential energy due to the spring. Let's put an F here to indicate that that's the final potential energy due to the spring. And then of course we have mgh, final. And that has to be equal to the same set of energy but the initials. So that's going to be 1/2 mvi squared plus 1/2 k delta x I squared plus mghi. So now I want to start putting in the variables from my problem into my equation here, but I actually have to make a little step before that. I have to make sure I totally understand what's the final state we're talking about and what's the initial state that we're talking about. So in order to understand, is there potential energy here? Is there potential energy there? I have to know what is the state of the system we're talking about. So the final state seems pretty obvious. It's when the ball has left the spring. So let me draw a picture of that just so we're totally convinced. I'm going to draw a picture like at the top, right? So this is like, here's the spring uncompressed with the ball flying off of it, VF. This is the final. So in the final state, the spring is not compressed. Delta XF is 0. And what about H? So VF is the thing I'm looking for. Well, in order to say what HF is, I have to say where my zero of gravitational potential energy is. And what I'm going to do is I'm actually going to take the bottom to be my H equals 0. So I'm basically using a coordinate system in which the 0 of the vertical axis is on the floor. I'm doing that sort of by suggestion because the problem has an H in it. So it seems to me to be kind of natural to measure from the floor. You could put H equals 0 at the top too. There's nothing wrong with doing that. But if you do that, you just have to be careful when you enter numbers like delta x for the height of the ball is actually below 0. So you have to put in negative numbers if you do that. I find that kind of confusing sometimes. So to keep all the heights positive, I'm going to select the floor as the H equals 0. If I do that, that means that the final height of the ball is going to be H, the 1.2 meters, because that's the distance that the ball is off the ground when it leaves the spring. Now the initial is going to be the spring compressed by a distance delta x. So that delta x, that is going to be the initial, the initial compression of the spring. So what the delta x in there is my delta xi. The ball is momentarily motionless at this very point, at this point right before it launches off the spring, so the initial speed is going to be 0, but now I need to figure out what the height is going to be. Well, the height is going to be a little bit lower than my final height, 1.2. It's actually going to be lower by that amount. So, and I can sort of indicate that by drawing a line straight over here, and then it should be pretty obvious that that height, that initial height, is going to be h minus delta x. So that's my initial height. So now I have a bunch of, I can now set all the parameters in my energy equation. So I can now come down here and rewrite my energy equation. And let's just be, so the initial velocity is 0, so that goes away. The final compression of the spring is 0, so that goes away. And those are all the things that should be 0, right? Yes, I'm looking for VF. Oh, yeah, so that should be it. So now I can copy down that equation, putting in all the decisions that I've made here. So nothing changes in my final kinetic energy. My final potential energy is now mgh, where that h is the 1.2. That's the potential energy due to the spring, where I've just put in my delta x squared in place of the compression of the spring. And then finally I have mg times my initial height, which was h minus delta x. So now I want to go about finding a solution, checking to see that I have all the right variables. I do indeed. This is my only unknown. I know mgh, I know 1/2 k delta x squared, I know mgh, I know delta x, so I should be able to solve this now. So I'm going to move mgh to the other side first. And you can see that I immediately have a cancellation, which is that if I distribute the mg into parentheses, I have an mgh right there, and I have an mgh right there. I should have a negative sign on that, right? Sorry, that's a mistake. That should be negative because I moved the mgh over to the other side. So there's a negative sign there. So this mgh here is going to cancel with the minus mgh there, and you're just going to have an mg delta x. And of course, that is what should have happened, because the only thing that should matter in this problem is the change in the gravitational potential energy, the change in the height. The absolute 0, where you put the 0, doesn't matter. So no matter what I did, the h had to drop out of that equation. And the fact that it did is evidence that I am doing the right thing. So first let me write down what that is after I observe that the mgh gets canceled. So there's that, 1/2 k delta x squared minus mg delta x. Now I want to go back over to my other side, divide by m and multiply times 2. You can see that when I did that, I got an m on the bottom. The 1/2 canceled because I multiplied times 2. In this term, the m went away, and the 2 got put right there, and so now I just have to take a square root of that thing. Right there, and if I plug that in, I should get 2.1 meters per second. So moving on to the second part of this problem, it says what is the maximum height of the ball? So there are several different ways that we can go about doing this, but of course we're going to start by doing conservation of energy, EF is equal to EI, and I'm actually going to repeat the exact same expression I had to start out with in the beginning, because it's the same 3 sources of energy that I need to decide if they're in my problem. And now I need to, again, be very careful. What is my initial state and what is my final state? You can do, basically you have 2 different options. You can either say that my initial state is given by this information, right? It's when the ball is actually being pushed down on the spring, because that was the initial state for A. The system hasn't changed while part A happens, so the total amount of energy is still the same from part A. So I can use the initial state from part A in part B. Or I can do after A, talk about what the system is doing after A, call that immediately the initial state for B, and then find the final state. I'm going to do the first thing. I'm going to say that I'm going to take the original state of the problem as what is happening, and then find the maximum height of the ball by assuming that that is the final state. So just to be clear, this, what I'm treating here is, this picture is the initial that I'm using still. The initial I'm going to use for A, for B, and hopefully for C. So the ball is still depressed a distance delta x on the spring. There's spring energy and there's also potential energy due to gravity. And I'm going to take the final state as the ball is right up here at the top, because that's where the ball is at its maximum height. So now let's think carefully about what those variables are. Well, I can copy over the variables from the initial state, meaning that the initial velocity is 0, the initial height is going to be h minus delta x, and the delta x initial is going to be delta x, the compression of the spring. So that we're going to use the same thing we used for the first part. That's part of why I did that, is so I could copy everything from the initial energy over to here. But here I also have to decide what the final speed is, but the final speed, right when it gets to its highest point, is going to be 0. It's going to stop instantaneously before it goes back down. So the speed is going to be 0 there. The final height is the thing that I'm looking for. That's, sorry, not 0, but that's my unknown. Question marks. And then I have to decide what the potential energy in the spring is, but of course the spring is like gone now, right? The ball left the spring in part A and isn't returning to it, so the compression of the spring is also going to be 0. So let me put that information into my problem. Yeah, I mean, I guess first let's just identify things that vanish. The final compression of the spring vanishes, the final speed vanishes, the initial speed vanishes, and I have everything else. So there's my potential energy due to gravity with the unknown HF that I'm going to solve for. There's the potential energy due to the spring with the compression 0.075. And there's the potential energy due to gravity initially, which is again h minus delta x. So now I simply want to solve for the final height, and I have to essentially do nothing now, just divide the whole thing by mg. So that's going to cancel an mg there and add some stuff here. But it's very easy to do that. And so my final answer is a bunch of stuff related to the spring, right? This is k delta x squared divided by 2mg plus h, which is 1.2, and minus that 0.075, which is the initial compression of the spring. And if you put that in, you should get about 1.42 meters. Now notice there's even more ways to solve this part than there is to solve part A. First, you could pick different initial positions. I picked before A. You could pick between A and B when there is only speed in the ball. You could also, because you can pick 0 of the height there, or maybe the 0 of the height there, like I did, you could maybe find the height of the ball above the spring. You just have to be very clear to indicate what are you talking about. If you find the height above the spring, you should probably say above the spring. Since I found from the ground, I'm going to write that very clearly, that I found the height from the ground, not from the top of the spring. Okay, let's go on to the third part. I should be able to do that pretty easily. How fast is the ball traveling when it hits the ground? Again, we have choices. We can pick the final, the final of B to be the initial of C. In fact, I could pick the initial of B, the final of A, or the initial of A, anything to be the initial for C, and then I have the final for C. Now, luckily, it's pretty easy to tell what is going to happen when the ball hits the ground as far as these three parameters, right? The final state is when the ball is right there. So the speed at which it hits the ground is what I'm looking for. The height at which it hits the ground is going to be 0. And remember, it's 0 because I'm picking right at the ground level to be 0. If you picked up here to be 0, you'd have to put in minus 1.2 to be the final height here. And again, because the spring is not connected anymore, the compression of the spring in the final state is 0. So the thing I'm going to do is I'm just going to copy down from my equation up here all the initial stuff, because nothing is changing about the initial. It's exactly the same for me for A, B, and C. But now for the final, I have to put in that the XF is 0. So that means using a different color to isolate what I'm talking about. That's 0 for part C. HF is 0 for part C, and so I just have a kinetic energy. So now I'm going to copy down that equation using the green set. So this is for C. I have my 1/2 m unknown VF squared on the left-hand side, and on the right-hand side I get the same stuff that I've been using for this entire problem. To solve that, I want to multiply times 2, divide by m, and that made m go in the bottom here, and it killed a factor of 1/2. I had to add a 2 in there to deal with the multiplying times a 2, and then I cut to kill the m in that term. And then finally I want to take a square root of that. And if I plug that into my calculator, I get about 5.29 meters per second as the speed of the ball right before it lands on the ground. So this is a pretty involved problem because there's these three multiple steps, but actually the equation we're using is relatively easy. It's just the conservation of energy equation with three separate terms for the energy. Remember the basic stuff? We're not just finding the energy at one location, we're always finding the change in energy between the final and the initial state. So you always should have an EF, an EF, and an EI. And also just be careful of the height. The height is the confusing aspect of this problem. It's not clear what height to use in any given part, and that's because it's your decision. There's not one answer. I'd say that I saw about a split in class today between people wanting to put the height at the bottom and people wanting to put the height at the top. Of course, other choices are possible too. You could pick the 0 to be right there, right where the ball is compressed to. I think that it adds an extra complexity because you're always carrying around this delta x. But I still had to carry around the delta x everywhere, so it doesn't matter. You'll get the same answers, but you do have to recognize that you are making a choice when you decide where the 0 of potential energy is going to be, and it's not necessarily right or wrong. And in fact, you can even maybe make multiple choices, right? I saw some people picking the 0 to be here in part A and then changing the 0 to be here in the later parts. That's kind of dangerous because not every physics problem can you change the coordinate system and expect the same thing to happen, but it does happen that for conservation of energy problems, it is kind of possible to do that. I think you should avoid that if possible, unless you really kind of know what you're doing, right? Okay, great. So this has been a solution to that whiteboard problem, spring from a table. I hope it has been helpful. Thanks for watching, and I'll see you next time.